So, how do you go about answering an interesting question? Now, the research process is broadly summarized here. You begin with an observation that you want to understand, and this observation could be anecdotal. Probably you have noticed that your dog eats your mayana plants, but not your cacti. That's a true story for us. Or could be based on some data. You've got several dog owners reported that their dogs eat their neighbor's mayana plant. Now, from your initial observation, you generate explanations or theories of those observations from which you can make predictions or hypotheses. Here's where the data come into the process, because to test your prediction, you need data. First, you collect some relevant data, and to do that, you need to identify things that can be measured. And then, you analyze those data. The analysis of the data may support your theory or give you cause to modify the theory. As such, the process of data collection and analysis and generating theories are intrinsically linked. Theories lead to data collection and analysis, and data collection and analysis informs theories. In this video, I will explain using Pinoy Big Brother, Coke, and Shopee the fun and often confusing research process. Now, the first step in the research process is to come up with a question that needs an answer. I spend rather more time than I should watching reality TV. Every year, I swear that I won't get hooked on Pinoy Big Brother, and yet, every year, I find myself glued to the TV screen waiting for the next contestant's meltdown. I am a psychology professor, so really, this is just research. I promise. So, one question I am constantly perplexed is why every year there are so many contestants with really unpleasant personalities. My money is on narcissistic personality disorder on the show. Now, a lot of scientific endeavors start this way. Well, not by watching PBB, but by observing something in the world and wondering why it happens. Having made a casual observation about the world, that is, Big Brother contestants on the whole have profound personality defects, I need to collect some data to see whether this observations is true, whether this observation is true, and not just a biased observation. To do this, I need to define one or more variables that I would like to measure. There's one variable in this example, the personality of the contestants. I could measure this variable by giving them one of the many well-established questionnaires that measure personality characteristics. Let's say that I did this and I found that 75% of contestants did have narcissistic personality disorders. These data support my observation. A lot of Big Brother contestants have extreme personalities. Now, the next logical thing to do is to explain this data. One explanation could be that people with narcissistic personality disorder are more likely to audition for Big Brother than those without. This is a theory. Another possibility is that the producers of Big Brother are more likely to select people who have narcissistic personality disorders to be contestants than those with less extreme personalities. This is another theory. We verified our original observation by collecting data, and we can collect more data to test our theories. We can make two predictions from these two theories. Now, the first is that the number of people turning up for an audition that have narcissistic personality disorder will be higher than the general level in the population, which is about 1%. A prediction from a theory like this one is known as a hypothesis. We could test this hypothesis by getting a team of clinical psychologists to interview each person at the Big Brother audition and diagnose them as having narcissistic personality or not. Now, the prediction from our second theory is that if the Big Brother selection panel are more likely to choose people with narcissistic personality disorder, then the rate of this disorder in the final contestants will be higher than the rate in the group of people for audition. Now, imagine that we have collected these data. In total, 7,662 people turned up for the audition. Our first hypothesis is that the percentage of people with narcissistic personality disorder will be higher at the audition than the general level in the population. We can see in this table that 7,662 people at the that the 7,662 people at the audition, 854 were diagnosed with the disorder. This is about 11%. That is 854 divided by 7,662 times 100, which is much higher than the 1% we'd expect. Therefore, hypothesis 1 is supported by the data. The second hypothesis was that Big Brother selection panel have a bias to choose people with narcissistic personality disorder. If we look at the 12 contestants that they selected, 9 of them had a disorder. That's a massive 75%. If the producers did not have a bias, we would have expected only 11% of the contestants to have the disorder. The data again supported our hypothesis. Therefore, my initial observation that contestants have personality disorders was verified by data. Then my theory was tested using specific hypotheses that were also verified using data. Data are very important if you think about it. I would now be smugly sitting in my office. No, I don't have an office here with a contented grin on my face about how my theories and observations were well supported by the data. Perhaps I would quit while I am ahead and retire. It's more likely though that having solved one great mystery, my excited mind would turn to another. After let's say another few hours, well, days probably, locked up at home watching PBB, I would emerge triumphant with another profound observation, which is that these personality disordered contestants, despite their obvious character flaws, enter the house convinced that the public will love them and that they will win. My hypothesis would therefore be that if I asked the contestants if they thought they would win, the people with personality disorder would say yes. Well, let's imagine I tested my hypothesis by measuring their expectations of success in the show. By just asking them, do you think you would win PBB? Let's say that 7 out of 9 of the contestants with personality disorders said yes, that they thought they will win, which confirms my observation. Next, I would come up with another theory. These contestants think that they will win because they don't realize they have a personality disorder. My hypothesis would be that if I asked these people about whether their personalities were different from other people, they would say no. So, as before, I would collect some more data and perhaps ask those who thought that they would win whether they thought that their personalities were different from the norm. All 7 contestants said, imagine that all 7 contestants said yes, that they thought their personalities were different from the norm. So these data seem to contradict my original theory. This is known as falsification. which is the act of disproving a hypothesis or theory. It is unlikely that we would be the only people interested in why individuals who go on Big Brother have extreme personalities and think that they will win. Imagine these researchers discovered that number one, people with narcissistic personality disorder think that that they are more interesting than others, and number two, that they also think that they say deserve success more than others, or that they also think that others say like them because they have special personalities. Now, this additional research is even worse in use for my theory. If they didn't realize that they had a personality different from the norm, then you wouldn't expect them to think that they were more interesting than others. And you certainly would not expect them to think that others will like their unusual personalities. In general, this means that my theory sucks. It cannot explain all of the data. Predictions from the theory are not supported by subsequent data, and it cannot explain other research findings. At this point, I would start to feel intellectually inadequate, and people would find me curled up in my desk in a flood of tears, wailing and moaning about my failing career. It's funny because I am like that right now. At this point, a rival scientist, say by the name of Michael Carmichael, appears on the scene with a rival theory to mine. In his theory, he suggests that the problem is not that personality disordered contestants don't realize that they have a personality disorder, or at least a personality that is unusual, but that they falsely believe that this special personality is perceived positively by other people. Put another way, they believe that their personality make them likable and not dislikable. One hypothesis from this model is that if personality disordered contestants are asked to evaluate what other people think of them, then they will overestimate other people's positive perception. To test this hypothesis, Carmichael collected yet more data. When each contestant came to the diary room, they had to fill out a questionnaire evaluating all of the other contestants' personalities, and also answer each question as if they were each of the contestants responding about them. So for every contestant, there is a measure of what they thought of every other contestant, and also a measure of what they believe every other contestant thought about them. He found, Carmichael found that the other contestants, or that the contestants with personality disorders did overestimate their housemates' view of them. In comparison, the contestants without personality disorders had relatively accurate impressions of what others thought about them. These data, irritating as it would be for me, support the rival theory that the contestants with personality disorders know they have unusual personality but believe that these characteristics are ones that others would feel positive about. So, in this regard, Michael Carmichael's theory is quite good. It explains the initial observations and bring together a range of research findings. So the end result of this whole process and my career is that we should be able to make a general statement about the state of the world. In this case, we could state Big Brother contestants who have personality disorders overestimate how much other people like their personality characteristics. So, We have seen already that data collection is vital for testing theories. When we collect data, we need to decide on two things: what to measure and how to measure this. So this video focused on the first of these issues. So to test hypothesis, we need to measure variables. As earlier mentioned, variables are just things that can change or vary. So they might vary between people. For example, IQ, attitudes towards the death of Aliana in Provinciano, or location, for example, unemployment, or even time. For example, mood, profit, number of cancerous cells. No. Now, most hypotheses can be expressed in terms of two variables: a proposed cost and a proposed outcome. For example, if we take the scientific statement, Coca-Cola is an effective spermicide, then the proposed cost is Coca-Cola, and the proposed effect is dead sperm. Both of the cost and the outcome are variables. So for the cost, we could vary the type of drink, and for the outcome, these drinks will kill different amounts of sperm. So the key to testing such statements is to measure these two variables. A variable that we think is a cost is known as an independent variable, because it is, or rather its value do not depend on any other variables. A variable that we think is an effect is called a dependent variable, because the value of this variable depends on the cost or the independent variable. These terms are very closely tied to experimental methods, in which the cause is actually manipulated by the experimenter. So, in cross-sectional research, we don't manipulate any variables, and we cannot make causal statements about the relationship between variables. So, it doesn't make sense to talk of dependent and independent variables, because all variables are dependent variables in a sense. One possibility is to abandon the term dependent and independent variables and use the term predictor variables and outcome variables. In experimental work, the cause or independent variable is a predictor, and the effect or dependent variable is simply an outcome. This terminology also suits cross-sectional work, where statistically at least we can use one or more variables to predict about the others without needing to imply causality. So the next thing that we have to talk about are, or rather, are levels of measurement. So, as we have seen in the example so far, variables can take on many different forms and levels of sophistication. The relationship between what is being measured and the numbers that represent what is being measured is known as the level of measurement. Now, broadly speaking, variables can be either categorical or continuous, and can have different levels of measurement. A categorical variable is made up of categories. A categorical variable that you should be familiar with already is your species. For example, human, or if you think you are a domesticated cat or a fruit bat or whatever you think you are a human or a cat or a fruit bat. You cannot be a bit of a cat and a bit of a bat, and neither a Batman nor, despite the many fantasies to the contrary, a cat woman. Not even one in a nice PVC suit. So, a categorical variable is one that names distinct entities. In this simplest form, just two distinct type of things. For example, male or female exist. This is known as binary variable. Other examples of binary variables are being alive or dead, pregnant or not, and responding yes or no to a question. In all cases, there are just two categories, and an entity cannot be placed into and an entity can only be placed only on one of the two categories. When two things that are equivalent in some sense are given the same name or number, but there are more than two possibilities, the variable is said to be nominal variable. So it should be obvious that if the variable is made up of names, it is pointless to do arithmetic on them. If you multiply a human by a cat, you do not get a hat. However, sometimes numbers are used to denote categories. For example, the numbers worn by players in a basketball team. These numbers do not tell us anything other than the players', let's say, favorite numbers. We could equally have jerseys with AD and LBJ instead of 3 and 23. A player wearing jersey number 10 is not necessarily better than a player wearing jersey number 1. It is equally as pointless to try to do arithmetic with nominal scales where the categories are denoted by numbers. You cannot tie together Alex Caruso wearing jersey number 4 with Wes Matthews wearing jersey number 9 and Jared Dudley who wears jersey number 10 using a packaging tape and somehow result in LeBron James who's wearing jersey number 23 in the process. Now, the only way that nominal data can be used is to consider frequencies. For example, we could look at how frequently number 23 dunks compared to number 4. So far, the categorical variables we have considered have been unordered. For example, different brands of Coke with which you're trying to kill sperm. But they can be ordered too, like increasing concentration of Coke with which you're trying to kill sperm. So, when categories are ordered, the values or the variables the variable is known as an ordinal variable. So, ordinal data tell us not only the things that things have occurred, but also the order in which they occurred. However, these data tell us nothing about the differences between values. Let's use Miss Universe 2018 as an example, where the three winners were Catriona, Tamarin, and Stephanie. The names of the winners don't provide any information about where they came in the contest. However, labeling them according to their performance does. First, second, and third. These categories are ordered. So, in using ordered categories, we now know that the woman who won was better than the women who came second and third. Still know nothing about the differences between categories though. We don't, for example, know how much better the winner was than the runners up than the runners up. So Catriona might be an easy victor, getting much higher ratings from the judges than Tamarin and Stephanie, or it might have been a very close contest that she won by only a point. Ordinal data, therefore, tell us more than nominal data. They tell us the order in which things happen, but they still do not tell us about the differences between points on a scale. The next level of measurement moves us away from categorical variables and into continuous variables. Now, continuous variable is one that gives us a score for each person and can take on any value on the measurement scale that we are using. The first type of continuous variable that you might encounter is an interval variable. So, interval data are considerably more useful than ordinal data, and most statistical tests rely on having data measured at this level. To say that data is interval, we must be certain that equal intervals on the scale represent equal differences in the property being measured. For example, on Shopee, customers are encouraged to rate their sellers on several dimensions. Each dimension, for example, product quality, seller service, or etc., is evaluated using a 5-point scale represented by stars. For this scale to be interval, it must be the case that the difference between product quality rating of 1 and 2 is the same as the difference between, say, 3 and 4 or 4 and 5. Now, similarly, the difference in product quality between ratings 1 and 3 should be identical to the difference between ratings of 3 and 5. Variables like this that look like intervals are treated as intervals are often actually ordinal. Now, ratio variables go a step further than interval data by requiring that in addition to the measurement scale meeting the requirements of an interval variable, the ratio of values along the scale should be meaningful too. For this to be true, the scale must have a true and meaningful 0 point. In our seller rating, this would mean that a seller rated as 4 would be twice as helpful as seller rated as 2, who would also be twice as helpful as seller rated as 1. Now, the time to respond to something is a good example of ratio variable. So, when we measure a reaction time, not only is it true that, say, the difference between 300 and 350 milliseconds as a difference of 50 milliseconds is the same as the difference between 210 and 260 milliseconds, or 422 and 472 milliseconds. But also, it's true that the distance along the scale are divisible. A reaction time of 200 milliseconds is twice as long as a reaction time of 100 milliseconds, and twice as short as a reaction time of 400 milliseconds. So, continuous variables can be, obviously continuous, but also discrete. This is quite a tricky distinction. A truly continuous variable can be measured to any level of precision, whereas a discrete variable can take on only certain values, usually whole numbers on the scale. So what does this mean actually? So, our example of rating sellers on a 5-point scale is an example of discrete variable. The range of the scale is 1 to 5, but you can enter only values of 1, 2, 3, 4, or 5. You cannot enter a value of, say, 4.32 or 2.18. Although a continuum exists underneath the scale, in this regard, a rating of 3.24 makes sense. The actual values that the variable takes on are limited. A continuous variable would be something like age, which can be measured in an infinite level of precision. You could be 34 years, 7 months, 21 days, 10 hours, 55 minutes, 10 seconds, 100 milliseconds, 63 microseconds, and 1 nanosecond old, if you think about it. So we have seen that to test hypothesis, we need to measure variables. Obviously, it's also important that we measure these variables accurately. Ideally, we want our measure to be calibrated such that values have the same meaning over time and across situations. Weight is one example. We would expect to weigh the same amount regardless of who weighs us or where we take the measurements, assuming it's on Earth and not in an anti-gravity chamber. Sometimes variables can be directly measured, such as profit or weight or height, but in other cases, we are forced to use indirect measures such as self-report, questionnaires, and computerized tasks, to name a few. Let's go back to our Coke as spermicide example. Imagine we took some Coke and some water and added them to two test tubes of sperm. After several minutes, we measured the motility, that is movement, of the sperm in the two samples and discovered no difference. A few years passed and say another scientist by the name of Dr. Maria Palad replicated the study but found that sperm motility was worse in the Coke sample. There are two measurement related issues here. That could explain her success and our failure. Number one is that Dr. Palad might have used more Coke in the test tube. Sperm might need a critical mass of Coke before they are affected. Or number two, Dr. Palad measured the outcome, that is motility, differently to us. The former point explains why chemists and physicists have devoted so many hours in developing standard units of measurement. If you had reported that you'd use 100 ml of Coke and 5 ml of sperm, then Dr. Palad could have ensured that that she had used the same amount, because milliliters are a standard unit of measurement. We would know that Dr. Palad used exactly the same amount of Coke that we used. Now, direct measurements such as the milliliter provide an objective standard. 100 ml of liquid is known to be twice as much as only 50 ml. Now, the second reason for the difference in the result between the studies could have been to do with how sperm motility was measured. Perhaps in our original study, we measured motility using absorption spectrophotometry, whereas Dr. Palad used laser light scattering techniques. Perhaps her measure is more sensitive than ours. There will often be discrepancies between the numbers we use to represent the things we're measuring and the actual value of the thing we're measuring. That is the value we would get if we could measure it directly. Now, this discrepancy is known as measurement error. For example, imagine that you know as an absolute truth that you weigh 73 kilograms. One day, you step on the bathroom scale and it says 70 kilogram. There is a difference of 3 kilograms between your actual weight and the weight given by your measurement tool, that is the scale. So, there is a measurement error of 3 kilograms. Although properly calibrated bathroom scales would produce only very small measurement errors, despite what we might want to believe when it says we have gained 3 kilograms. So, self-report measures do produce measurement errors because factors other than the one you're trying to measure will influence how people respond to our measures. Imagine you were completing a questionnaire that asked you whether you had pooped in a school lavatory. If you had, would you admit it or might you be tempted to conceal the fact? So, the next thing that we have to talk about when gathering data are, well, validity and reliability. One way to try to ensure that measurement error is kept to a minimum is to determine properties of the measure that give us confidence that it is doing its job properly. The first property is validity, which is whether an instrument actually measures what it sets out to measure. The second is reliability, which is whether an instrument can be interpreted consistently across different situations. Validity refers to whether an instrument measures what it was designed to measure. A device for measuring sperm motility that actually measures sperm count is not valid. Things like reaction time and physiological measures are valid in the sense that a reaction time does in fact measure the time taken to react, and skin conductance does measure the conductivity of your skin. However, if we're using these things to infer on other things, for example, using skin conductance to measure anxiety, then they will be valid only if there are no other factors other than the one we're interested in that can influence them. Criterion validity is whether the instrument is measuring what it claims to measure. For example, does Shopee product rating scale actually measure product quality? So, in an ideal world, you could assess this by relating scores on your measure to real-world observations. For example, we could take an objective measure of how good products were and compare these observations to customer ratings in Shopee. This is often impractical, and of course, with attitudes, you might not be interested in the reality so much as the person's perception of reality. Well, you might not care whether they are a psychopath, but whether they think they are psychopaths. So, with self-report measures and questionnaires, we can only assess the degree to which individual items represent the construct being measured and cover the full range of the construct, that is content validity. So, validity is a necessary but not sufficient condition of a measure. A second consideration is reliability, which is the ability of the measure to produce the same results under the same condition. To be valid, the instrument must be first reliable. The easiest way to assess reliability is to test the same group of people twice. So, a reliable instrument will produce similar results at both points in time. This is called test-retest reliability. Sometimes, however, you will want to measure something that does not vary over time. For example, or does vary over time. For example, you have moods, or blood sugar levels, or let's say productivity. So, statistical methods can also be used to determine reliability in this regard. The final stage of the research process is to analyze the data you have collected. When the data are quantitative, this involves both looking at your data graphically to see what the general trend in the data are and also fitting statistical model to the data. So, once you've collected some data, a very useful thing to do is to plot a graph of how many times each score occurs. So, this is known as a frequency distribution or histogram, which is a graph plotting values of observations on a horizontal axis with a bar showing how many of each values occur in the dataset. Frequency distribution can be very useful for assessing properties of the distribution of scores. Also, we get further away, as we get further away from the center, the bar gets smaller, implying that as scores start to deviate from the center, their frequency is decreasing. So as we move still further away from the center, our scores become very infrequent. So the bars are very short. So many naturally occurring things have this shape of distribution. For example, men in the Philippines are about 5 feet 4 inches tall. So some are a bit taller or shorter, but most cluster around this value. There will be very few men who are really, really tall. For example, above 6 feet 10 inches. Or really, really short. For example, under 4 feet. There are two main ways in which a distribution can deviate from normal. So as you can see in this graph, this is an example of normal distribution. This is actually a joke. There's no such thing as paranormal distribution. But there are two main ways in which a distribution can deviate from normal. That is lack of symmetry, called skew, and pointiness, called kurtosis. So, skewed distributions are not symmetrical, and instead the most frequent scores, the tall bars on the graph, are clustered at one end of the scale, as seen in these examples. So the typical pattern is a cluster of frequent scores at one end of the scale and frequency of scores tailing off towards another end of the scale. A skewed distribution can be either positively skewed, where the frequent scores are clustered at the lower end and the tail points towards the higher or more positive scores, or negatively skewed, as seen here, where the frequent scores are clustered at the higher end and the tail points towards the lower end or more negative scores. So, distributions also vary in their kurtosis. So, kurtosis, despite sounding like some kind of exotic disease, refers to the degree to which scores cluster at the end of the distribution, known as the tails. So, and how pointy a distribution is. So, a distribution with positive kurtosis has many scores in the tails and so-called heavy tail distribution, and is pointy. So this is known as leptokurtic distribution. So this is an example of leptokurtic distribution. So in contrast, a distribution with negative kurtosis is relatively thin in the tails, has light tails that is, and tends to be flatter than normal. This distribution is called platykurtic. So here's an example of, what a platykurtic distribution would look like. So this distribution is called platykurtic, and ideally, we want our data to be normally distributed, that is not too skewed and not too many or too few scores at the extremes. In a normal distribution, the values of skew and kurtosis are 0. That is, the tails of the distribution are as they should be. So, if a distribution has values of skew or kurtosis above or below 0, then this indicates a deviation from normal. So the next thing that we have to talk about are the centers of distribution, and we can use most More often we use three of this, or there are three types of this. We have the mean or the average of data set. And it's found by adding all numbers in the data set and then dividing by the number of values in the set. We also have the median, and it is the middle value when a data set is ordered from least to greatest. And we have the mode, and this is the number that occurs most often in a data set. So, having looked at your data, the next step is to fit it to a statistical model to fit a statistical model to the data. So I want to talk here briefly about two very important types of hypothesis. So that we are using in analyzing data. So scientific statements, as we have seen, can be split into testable hypotheses. The hypothesis or prediction that comes from your theory is usually saying that an effect will be present. This hypothesis is called the alternative hypothesis and is denoted by H1. It's sometimes called the experimental hypothesis, but because this term relates to a specific type of methodology, that is, well, the experimental method, it's probably best to use alternative hypothesis. So there is another type of hypothesis, though, and this is called the null hypothesis and is denoted by H0. This hypothesis is the opposite of the alternative hypothesis, and so would usually state that an effect is absent. So, taking our Pinoy Big Brother example earlier, we might generate the following hypothesis. For the alternative hypothesis, Big Brother contestants will score higher on personality disorder questionnaires than members of the public. And for your null hypothesis, you have Big Brother contestants and members of the public will not differ in their scores on personality disorder questionnaires. So the reason that we need the null hypothesis is because we cannot prove the experimental hypothesis, or in this regard, alternative hypothesis, using statistics, but we can reject the null hypothesis. In our data, if our data gives us confidence to reject the null hypothesis, then this provides support for our experimental or alternative hypothesis. However, you have to be aware that even if we can reject the null hypothesis, this doesn't prove the experimental or the alternative hypothesis. It merely supports it. So, rather than talking about accepting or rejecting a hypothesis, which some textbooks tells you to do so, or some professors tell you to do so, we should be talking about the chances of obtaining the data we've collected, assuming that the null hypothesis is true. So, using our Big Brother example, when we collected data from the auditions about the contestants' personalities, we found that 75% of them had a disorder. When we analyze our data, we are really asking, assuming the contestants are no more likely to have personality disorders than members of the public, is it likely that 75% or more of the contestants would have personality disorders? Intuitively, the answer is that the chances are very low. If the null hypothesis is true, then most contestants would not have personality disorders because they are relatively rare. Therefore, we are very unlikely to have got the data that we did if the null hypothesis were true. What if we found that only one contestant reported having a personality disorder? That's about 8%. So, if the null hypothesis is true and contestants are no different in personality to the general population, then only a small number of contestants would be expected to have a personality disorder. The chances of getting these data, if the null hypothesis is true, are therefore higher than before. So when we collect data to test theories, we have to work in these terms. We cannot talk about the null hypothesis being true or the experimental hypothesis being true. We can only talk in terms of the probability of obtaining a particular set of data if, hypothetically speaking, the null hypothesis was true. So, we will elaborate on this idea in the following weeks. So if you don't, if you haven't yet understood what I meant by that, we will talk more about this in the coming weeks. Don't worry about that. So, finally, hypothesis can also be directional or non-directional. A directional hypothesis states that an effect will occur, but it also states the direction of the effect. For example, readers will know more about research methods after, say, reading a particular chapter. Or let's take this video as an example. Say our hypothesis states that viewers will know more about research methods after watching this video. It's a one-tailed hypothesis because it states the direction of the effect. Viewers will know more. A non-directional hypothesis states that an effect will occur, but it doesn't state the direction of the effect. For example, viewers' knowledge of the research methods will change after they have watched this video. Does not tell us whether their knowledge will improve or get worse. So, what have you discovered about statistics in this video? Well, actually not a lot because we haven't really got into the statistics bit yet. However, we have discovered some stuff about the process of doing research. We began by looking at how research questions are formulated through observing phenomena or collecting data about a hunch. Once the observation has been confirmed, theories can be generated about why something happens. From these theories, we formulate hypotheses that we can test. To test hypotheses, we need to measure things, and this leads us to think about the variables that we need to measure and how to measure them. Then we can collect some data. The final stage is to analyze these data. In this video, we saw that we can begin by just looking at the shape of the data, but that ultimately we should end up fitting some kind of statistical model in the data. So in short, the reason that your evil statistics professor is forcing you to learn statistics is because it is an intrinsic part of the research process and gives you enormous power to answer questions that are interesting. Again, this has been Dex Kamitan, and thank you for watching.